Hello, grade 12s. Take a look at my blank paper. I'm going to do an interesting lesson with you today, and believe it or not, this lesson you're not going to have direct homework from today, but you will be introduced to related concepts through the rest of the chapter. What I'm actually going to start with is something not even related to things that we've been learning. I want to talk about the concept of compound interest. This world revolves around money, making money, and one of the most important ways that our money grows quickly is by earning compound interest. What does that mean? It means you can put $1,000 in the bank. If the bank pays 3% interest per year, per annum, which isn't unreasonable for some accounts these days, the money could be compounded. And for example, if the bank were to compound the interest twice a year, what it means is that at 6 months, they would figure out how much interest they owe you. They would give it to you. The money would sit in the bank, the larger amount, for another 6 months. And at the end of the year, you'd have more money than you started with. But there's a terrific little formula that calculates how much money you would have at the end of the year. The principal is the amount that you originally invest. And we said, let's invest $1,000. R represents the interest rate, but it has to be expressed as a decimal, and it's the interest rate per compounding period. In other words, I said to you that I want to compound this every 6 months. So in that case, my interest rate would be 1.5%, because that's 3% divided by 2 if you're going to do it twice a year. And as a decimal, that's 0.015. So you can use this little formula because what it allows you to do is figure out how much money you would have at the end of a year. You put $1,000 where the P goes. You put the 0.015 because that's the interest rate per compounding period for 6 months. And of course, if money is compounded twice a year, then I would put a 2 here for the total amount of times it's compounded. And so when you punch that out, you would have 1,000 times 1.015 to the exponent 2, and you would have $1,030.23 at the end of the year. And that $30 is pure interest. Now imagine if you put that money in the bank for another year and let it grow. Of course, it's going to grow faster and faster. And that's how rich people get rich. Their money earns interest for them. But I want to take a look at this idea. I'm actually going to put this piece of paper under the camera where I already have it typed out, okay? What we're going to do is we're going to invest only $1. So our P is going to be 1. This is to make a point. I'm going to change how many times the money is compounded to show you how it would grow. And we're going to use 100% as an interest rate, which might seem absurd. But basically, it means that if you put $1 in the bank and you let it sit there for the whole year, you would earn 100% interest, which is 1.00, and you would have $2 at the end of the year because you would have your original dollar plus the dollar you just earned in interest. So it may seem like a funny interest rate, but watch what happens when I change the compounding period. What if the money was compounded twice a year, like the example I just did? My R is going to be 100%, which is the decimal 1.00. But of course, that's going to change from question to question because it has to be per compounding period. So if it's twice a year, I divide the 1 by 2, and that's where this half comes from. And then, of course, it's compounded twice through the year. And look, because it was compounded more often, I earned more money than only compounding it once a year. If you compound it every month, then basically you're going to take R, which is 1, and divide it by 12 every month, which means you'll be doing it 12 times a year. And look what happens, $2.61. The more often you compound it, the more money you're going to make. And that's what this formula, A equals P times 1 plus R to the n, helps people calculate. I want to increase the frequency with which the interest is calculated. So now I'm going to say, let's do it every day. You've heard of daily interest savings accounts? Well, that's what they do. Every day, the computer calculates how much interest they owe you. They do that 365 times. They actually give you that money, I think it's every 3 months, but here's how it works. I take the 1, which is R, but because I'm doing it daily, I divide by 365. And that means I will do it 365 times through the year. And now I'm up to $2.71, but I'm maintaining decimals. What if you did it every minute? This is a hypothetical situation. 24 hours a day, 365 days a year, 60 minutes per hour. That's your denominator. And then that becomes your numerator. And then you get this number, 2.7182. So now we go into the world of theoretical mathematics. And what if we increase the frequency with which we are calculating the interest, and we say we're going to do it infinite number of times? What you have here is this exact formula, but you put infinity, which isn't a number, it's a concept, and you put that I'm doing it infinite times. And then you see I wrote this little e here. Okay, I'm going to develop this a little further. You can't do a numeric calculation. If you want to see how much money you're going to have at the end of a year, if they sort of continuously calculate interest and give you interest infinite times. The only way you can calculate this expression is the concept of a limit. And this is what it would look like. I'll put X's here. And the way you can manually calculate limits is you make a table of values and you literally, this is the Y, oops, don't want that, to the X. You let X get larger and larger and larger. You let X go to infinity and you see what happens. And so I did this already. I put 100 here and this number was 2.7048, okay? Then I put 1,000 and I got 2.7169 when you work this out. So then I put 10,000, 2.7181. Then I put 1,000,000, 6 zeros there, I get 2.7183, and then I added an extra 0, and I rounded it, and I got 2.7183. That number is called Eulers number. Eulers number. I think it's pronounced Euler. Eulers number. Euler was a mathematician, and his discovery of this number is named after him. This is a decimal that actually extends infinitely. Like pi. It's an irrational number, but E has huge, huge, huge ramifications in the world of mathematics. And it's a super important number. And this is the reality of what E, where it comes from, how it exists. This is one of the ways that we look at it, but this is called Euler's number. So it's a new number that you can add to your repertoire, and we're going to start to learn to work with it in calculus. You can even see that on many calculators, yours included. I don't know if you can see it that well, but I have an E to the X button, which serves as an E button. So if I wanted to know what E was by punching it into my calculator, I would hit that button. Let me clear this so you can see. And I would say E to the exponent 1 because I just want to see what E is. And there it is as a decimal. That's a lot of places. So now you've been exposed to a brand new number called Euler's number. It's a little deep. I don't expect you to really understand it. And this is not something we're actually doing in our course. But what I'm going to do is leapfrog from here. And we're going to start to learn to work with this and incorporate it. Now, the first thing you have to wrap your head around is E is just a non-ending, non-repeating decimal that's about 2.718. Just the way you know pi is approximately 3.14, now you know E is approximately 2.718. I'm going to show you another application of this, though, and this has direct connection to our course. And this is really cool, you guys, because now, given the pandemic, and all the sorry, that's on my scrap paper, and everything that's been going down related to the pandemic, we can actually have some direct implications to our mathematics because, you know, you keep hearing them talk about the growth of the virus, you know, of this coronavirus spreading, and they say it's growing exponentially. And we've all heard of the expression to grow exponentially. And what growing exponentially means, it's if you take something like y equals 2 to the x, we know that that's an exponential function. But that's not exactly what exponential growth means. What exponential growth means is if the base, meaning the population, grows, the growth of that population, as it gets bigger and bigger, the growth gets faster and faster. So it's when something grows and it is related to the size of the population that's growing. It's how things grow in relation to their own size, proportionately. So when you have this population and they spread the coronavirus, then you have a bigger population, it's going to spread faster, and then bigger, and then bigger. And so the spread is exponential because the rate of growth is actually proportional to the value of the quantity that's growing, which is exactly the kinds of ideas we're going to talk about now in calculus. So it's all about exponential growth. Okay, so what I'm going to do is I'm going to just talk about these exponential functions. The base can change. That's not so important. It's still an exponential function. What defines it is the fact that the exponent is where our independent variable is. And we know, we've learned these things. We know what they look like. We know where the x and y intercept is. We know the domain. We know the range. We've studied these. But we've never done the derivative of these. Now, we don't know the formula for derivative. So what I'm going to do for you is I'm going to take you back to what we did right at the beginning of the course, and I'm going to find the derivative of y equals 2 to the x, but I'm going to have to do it from first principles. So what does that mean? Remember the limit as h goes to 0 of f of x plus h. Remember this way back. Only this time my function is 2 to the x. And so if I use this definition with this function, I should be able to calculate the derivative, because remember the answer to this is the derivative. Now we've never done a function like this, so this is the first time. So what I'm going to do is take the limit as h goes to 0 of 2, but here I put x plus h, and here I put x, and of course down here I have h. Now what I want to show you in order to work this out is I'm going to factor out 2 to the x. They both terms have it in the numerator. And if you factor it out, okay, I'll put a 1 here. Can you guys figure out what goes here? Because remember, it's this exponent. Take away the power you pulled out. That's the kind of work we were doing this year. So x plus h, take away the x, leaves h. And if you were to multiply it back, you would get 2 to the x plus h. And so I factored out. Why do I do that? Because if you're evaluating a limit as h goes to 0, it has absolutely no bearing on this. Not connected, nothing to do with it. So you could actually pull it, this is the properties of limits, pull it out and just evaluate this thing. Okay? Now how do you evaluate this? I mean, we don't have any tricks for it. You really just create a table of values and take numbers that get closer and closer to 0. For example, if I make my table of values, this is the mechanical, slow, long, hard way of evaluating a limit. You literally keep trying values. So here is 2 to the h minus 1 all over h. So I'm going to take a small number that's pretty close to 0, like 0.1. I'm going to pop it in and work what 2 to the 0.1 minus 1 over 0.1 is, and because I'm a genius and I know it's 0.71773. I'm then going to take another number even closer to 0, like 0.01, and see what value I get. And if you keep doing this and you start to see a pattern of numbers here, you're going to actually be able to evaluate the limit, and this expression is really just some number, some numeric value, whatever the answer is. So of course I've already done it. Let's take a look at this. So on this piece of paper, I said I'm going to find, using first principles, the limit, right, as of 2 to the x as h goes to 0. And so I did up here the same steps that I just did with you, where I plugged it in, factored the 2 to the x, put it out front. And so here is my table of values where I am trying to work out this numeric quantity. See, what is this limit? To evaluate it manually, I did all the work for you. You put in 0.01, this is what comes out of this. You put in 0.001, and you keep working this expression out with tinier and tinier numbers, and you can see a pattern. It's clearly approaching 0.69315. I'm going to round that off to 0.69, and I'm going to say, you know what this expression works out to? Believe it or not, 0.69. I mean, that's an approximation. So if y is 2 to the x, and I just found the derivative from first principles, that's what I get for the derivative, approximately. Okay? So that's the way I got the derivative of an exponential function. I did it through first principles, but I want to show you something kind of cool. I'm going to do it about 2 or 3 more times. Only I'm not going to do it because I've already got it done for you. This time I'm going to let the base of my exponential function be 2.5. So the object of the game here is to find out the derivative of this exponential function, 2.5 to the x. So I do the same thing. I use first principles, and instead of factoring out the 2, instead of having 2's here, I have 2.5's. And if you mechanically run through the steps, there it is, no matter what the base is. You always get this 2.5 to the x out front, and this ends up being the quantity, just like the one we did before, except of course now the base is 2.5. And again, I'm going to mechanically calculate this numeric value by putting in smaller and smaller numbers, and you can see that the limit as h goes to 0 of this expression is 0.916. Or if I round it to 2 places, I could put 0.92, right? So if y is that function, the derivative, remember Leibniz notation, would be y prime equals 0.92 times 2.5 to the exponent x. I'm going to do another one manually. Obviously, eventually, we're going to teach you how to get derivatives without the manual, slow first principles method, but I'm trying to make a point here, so bear with. I change the base to 2.6. I do the same process over again. This time I'm evaluating this limit. So I put these values into this expression, and now I can see I've got 0.96, let's say, if I round it to 2 places. So if y is this particular exponential function, 2.6 to the exponent x, the derivative would be 0.96 times 2.6 to the x. So it looks like every time I take an exponential function, whether it's 2 to the x, 2.5 to the x, 2.6 to the x, I get a constant, some kind of number here, and then the original function. So you can see a pattern evolving. This was the derivative of 2 to the x. It was 0.69, 2 to the x. Here's the derivative for 2.5 to the x, 0.92, 2.5 to the x. And then when I bump it up, it's 0.96. So you see what's happening to these values? All right, we're going to do it again on the back. This time I'm going to let the base be 2.7, and look at this. When I evaluate this limit mechanically and slowly, I get 0.99. So the derivative of 2.7 to the x is going to be 0.99 times 2.7 to the x. Now I do it one last time, where the base is 2.71828. Looking familiar? That's Euler's number. So look what happens when I do the derivative of this function where the base just happens to be this new number, Euler's number. I do it the same way, so I have the exact same expression, except instead of the 2 or the 2.5, I have this guy. To evaluate the limit manually, I have to put in these values to the expression. These are the answers, and look what number this limit works out to be, 1. So when I get the derivative of Euler's number to the exponent x, I get 1 times 2.71828 to the x, meaning if y is 2.71828 to the x, the derivative is the same function as what we started with. And that, my friends, is one of the weird properties of Euler's number, amongst many other things. So basically, in a nutshell, if you want to summarize it, if you have an exponential function where the base is Euler's number, you can use this little e. Everybody knows that means Euler's number. Everybody now knows that that's approximately this decimal. And so we can have an exponential function that looks like 2 to the x, 4 to the x. Don't forget, we could have fractional bases. Now we have a new one, e to the x. You have to remind yourself, don't freak out when you see it. It's really just like writing 2.718 to the exponent x. But this is going to get thrown into our category of exponential functions. And that's the topic we're moving into in this next chapter. We're going to be studying exponential functions like all of these and finding their derivatives, obviously not through first principles. We'll show you the fast way to get it. But there's another exposure to Euler's number as a way to set the stage for the new unit.